Welcome to the Norwegian Academy of Science and Letters here in Oslo, Norway. And we're here because every year the Academy of Science and Letters hands out the Abel Prize, a very prestigious mathematics prize designed to celebrate and reward mathematicians who've made significant contributions to the world of mathematics. And today we're going to find out who the 2024 winner is.
As the president of the Norwegian Academy of Science and Letters, it's my pleasure and privilege to announce the winner of the Abel Prize for 2024. The board of the Norwegian Academy of Science and Letters has decided to award the Abel Prize for 2024 to Michel Talagrand for his groundbreaking contributions to probability theory and functional analysis, with outstanding applications in mathematical physics and statistics.
The Abel Prize honors outstanding scientific work in the field of mathematics. This year, we honor Professor Michel Talagrand from the Centre National de la Recherche Scientifique.
Dear Professor Talagrand, I would like to extend my sincere congratulations to you on your great achievements through your work on probability theory and functional analysis. The Abel Prize is a celebration of you as a mathematician and of the whole field of mathematics.
Norway is a knowledge nation. We depend on research-based knowledge and expertise to understand and resolve the challenges facing society. In this context, the Abel Prize is important to celebrate excellence in research. On behalf of the Norwegian government, congratulations as the Abel Prize Laureate for 2024, and welcome to Oslo, and welcome to Norway in May.
The Abel Prize winner is selected by an international group of esteemed mathematicians who draw from the nominations sent in by the mathematics community. To explain exactly why they picked Michel Talagrand as the 2024 Abel Prize winner, we will have a full reading of their citation by the chair of the board, Hilge Holden.
Thank you very much, Matt. The Norwegian Academy of Science and Letters awards the Abel Prize 2024 to Michel Talagrand, Centre National de la Recherche Scientifique, Paris, France, for his groundbreaking contributions to probability theory and functional analysis, with outstanding applications in mathematical physics and statistics. The development of probability theory was originally motivated by problems that arose in the context of gambling or assessing risks. It has now become apparent that a thorough understanding of random phenomena is essential in today's world. For example, random algorithms underpin our weather forecast and large language models. In our quest for miniaturization, we must consider effects like the random nature of impurities in crystals, thermal fluctuations in electric circuits, and the coherence of quantum computers. Talagrand has tackled many fundamental questions arising at the core of our mathematical description of such phenomena. One of the threads running through Talagrand's work is to understand geometric properties of high-dimensional phenomenon and to crystallize this into sharp estimates, with broad scopes of applicability. This led him to obtain many influential inequalities. For instance, Talagrand derived powerful quantitative results to prove the sharp threshold phenomena that often appear in the study of phase transitions in statistical mechanics. He also obtained a useful inequality bounding the quadratic transportation cost distance between a probability measure and a Gaussian distribution by their relative entropy. Much of Talagrand's work concerns the geometry of stochastic processes. A classical problem going back to Kolmogorov, arising for instance when one wants to analyze regularity properties of stochastic processes, is to estimate the supremum of a large collection of correlated random variables. Building on the work of Fernique and Dudley, Talagrand developed his theory of generic chaining, which provides sharp upper and lower bounds on the expectation of suprema of Gaussian processes. This illuminated the mysterious connection between the distance function on the underlying index set, determined by the covariance of the process and the expectation of its supremum. A key result in probability theory is the law of large numbers, asserting that the normalized sum of independent random variables converges towards its mean. This normalized sum is therefore concentrated using the terminology coined in the early work of Millman, or self-averaging using physics terminology. It was gradually realized that concentration is ubiquitous, since many random variables defined as function of a large number of independent random variables appear to be close to the mean with high probability. In an amazing tour de force, Talagrand provided quantitative versions of this phenomenon that hold in great generality, including the case of discrete random variables. This result applies to functions of independent variables that are Lipschitz with respect to the Euclidean metric and convex, yielding one of the several celebrated Talagrand inequalities. It laid the groundwork for a non-asymptotic theory of independence applicable to high-dimensional statistical problems. Since the work of Edwards and Anderson, physicists have been fascinated by the complex behavior exhibited by disordered systems, which describe phenomena like magnetization in the presence of inequalities, and more recently also the energy landscape arising in machine learning. In 1980, Parisi, Nobel Prize in Physics 2021, proposed an expression for the free energy of one of the simplest models of this type, namely the Sherrington-Kirkpatrick model. Guerra showed rigorously that this formula is an upper bound for the free energy. In a groundbreaking article, Talagrand proved a complementary lower bound, hence completing the proof of the Parisi formula. This provided the foundation for the development of a mathematical theory of spin glasses and its applications in statistical learning. Talagrand also obtained a rich variety of important results in measure theory and functional analysis. To cite only the most recent one, he answered a long-standing question by von Neumann and Mahaman in the negative by showing that there exist submeasures which are exhaustive but not absolutely continuous with respect to any finite additive measure. This fact implies the existence of radically new Boolean algebras. Talagrand is an exceptionally prolific mathematician whose work has transformed probability theory, functional analysis, and statistics. His research is characterized by a desire to understand interesting problems at their most fundamental level, building new mathematical theories along the way. He disseminated many of his insights in the form of very influential research monographs. Combining technical virtuosity with deep analytical and geometric insights to construct new powerful tools and answer long-standing hard questions, Michel Talagrand has had and continues to have an enormous impact on mathematics and its applications.
Thank you, Helge. Now, what struck me about the citation is the mention of how Talagrand was obsessed with understanding things at their most fundamental. And I believe that was a motto he took very seriously.
Yes, a guiding principle throughout his work has been a piece of advice that he got from his PhD advisor, Gustave Choquet. Choquet said that you should simplify the problem as much as possible while still keeping the intrinsic structure, and then try to understand it at that level. And this is what Talagrand has done throughout his career. You break down the problem to the simplest possible terms, then you extend, expand, and make it into a theory. And then, once you have understood it, you write a book about it. Take, for instance, the example of generic chaining. Talagrand studied this for 15 years. And now he has simplified it so that he says that you can understand it in 10 minutes. And of course he wrote a book about it.
Now, this approach of understanding things in their most simple context, did that affect when he was working in other research areas?
Yes, he tried to follow the same principle when he studied spin glasses. Here there was a formula based on physical intuition proved by Parisi, but Talagrand wanted to understand this in mathematical terms. So he wanted to have a fully rigorous mathematical proof of the Parisi formula. So now we have two arguments for the Parisi formula, one based on physical intuition and another one based on mathematical rigor. And of course, Talagrand wrote 2 volumes about it.
Always ends by writing a book. I think it's fantastic he was able to prove the same thing from physics, but by ignoring the physics largely and just looking at it mathematically. In fact, I'm now going to try and provide some extra context to the research that Talagrand was doing, but I've very much taken their motto to heart, and I'm going to try and do that in the situation which is the most simple situation possible while things still technically make sense. The first two concepts I would like to unpack from the citation is the idea of randomness and having a distribution. Now, randomness I can simplify down to rolling a dice, something we're all reasonably familiar with. I roll this and I get, a 2. Anyway, one of the 6 possible values on the dice picked at random. Now, in terms of distributions, Talagrand's work covered a lot of different types of distributions, but the most common and arguably the most important is something called the Gaussian distribution. This is a symmetric distribution where you have the most common event or value right in the middle, and then less likely events and values on either side. And this kind of Gaussian process comes up all over the place in the world around us. The mass that babies are when they're born, the scores people get at school, or even the age that people retire at. These may seem like they're random values, but they're all drawn from a Gaussian distribution. We can now try and combine both of those together so we can take random values from a Gaussian distribution. Now, if I roll 2 dice at the same time and then add their values, all the values are no longer equally likely. In this case, I just got an 8. And if you look at the distribution of the possible values and how likely they all are, it's close to a Gaussian distribution, but not quite. Although the more dice that I roll at once, the closer the distribution of these random values gets to a Gaussian distribution. So I can simulate picking a random number from the true Gaussian distribution by taking, I'm not going to show you how many, an unknown number of dice. I'm going to roll them behind this screen, and I'm going to tell you that this Gaussian distribution just gave us a value of 30. A value of 30. How many dice do I have? What is the largest possible value I might roll if I roll this another 10 times? There's a lot of questions you can ask about getting a random number from a Gaussian distribution. I can now tell you the second value out is 30. It's going to be bigger this time. 42. There you are, 42. And a lot of Talagrand's work was taking a random variable like this, where it's coming from a distribution, and you're getting some values from that random distribution, and you're asking questions. What's the average value? What is the suprema? What's the largest value I would get over a certain amount of time? And I can now reveal I was rolling, in this case, let's have a look here, 6, 9, 11. 11 dice. So the average value from that, the mean would have been 38.5. And we mentioned the law of large numbers in the citation. And that says if I was to keep rolling these dice, or taking random values from a Gaussian distribution, the average value from the results will converge with the true average value of the underlying distribution. However, life is not always quite as simple as a single Gaussian distribution. In the citation, you will have heard mention of higher dimensional spaces, and you're thinking, well, how are we going to get from a probability distribution to that? Well, that's what happens if we start combining a couple of these together. I'm going to go even more simple now with just flipping a coin. So I've got a yellow heads and a copper-colored tails. If I flip one coin, our first random value, is a tails. Now that's from a very simple distribution of 2 possible values, but bear with me. I'm now going to flip a second coin that will give us, heads. Very pleasing that it's different. And our final third one is heads. So now I'm selecting random values from different distributions, and I've ended up with tails, heads, heads. That's one of 8 possible values that could have come out of that process. To understand those 8 values and the way these 3 different, admittedly very simple distributions interact, we could label the corners of a cube with those 8 different outcomes. So I'm now using the X or the across axis as the first coin I flipped. I'm using the Y or the back axis for the second one, and the Z, the third axis, for the third value. And so now, when I pick these 3 values from 3 different distributions, what I'm doing is selecting a corner from a cube in 3 dimensions. If instead of being very discrete distributions with just 2 possible values, these could have been continuous distributions. They could be Gaussian, they could be something different. They don't all have to be the same, and each one is in an orthogonal, a new dimension from the others. So if I had 4, 5 more possible random distributions I'm pulling values from that are all interacting and being combined, the resulting space, the total probability distribution that we need to understand to be able to calculate expectations and values is a fairly confusing multi-dimensional object. The problem with higher dimensional spaces and shapes is they're kind of beyond human intuition. They're very hard to understand, but we do need to understand them. Just like when I was rolling 2 dice, the height of that distribution, or you could argue the area of that part of like a bar chart, that represents the probability of getting that value. The same thing holds in higher dimensions. We need to understand the volume, the hypervolume, some measure of how much there is in different areas of the distribution to work out the probabilities, and that is not straightforward. So I've got one of my favorite examples of how trying to understand higher dimensional shapes is difficult. And we're going to start in 2 dimensions. We're going to start with a square, and then I'm going to fill that square with unit circles or unit discs because they're filled in. You can think of these as the 2D version of like a solid ball. Now inside those unit discs, I'm going to put the biggest disc possible that will fit. It's not very big, it's about 0.414 compared to the radius of our unit discs. But we can, use Pythagoras and we can carefully calculate exactly how big that disc is. Let's go up a dimension. We've now got a cube-shaped box and we're going to fill that with 8 unit balls. They've all got a radius of 1. And once again, we can see how big a 3D ball can we fit right in the middle. And this time, that ball from the center is just over 0.7 compared to the unit balls. It's a bit bigger, which kind of makes sense. There's a bit more room to move, and you might think as we go up in dimensions, the ball gets a little bit bigger, but ultimately remains bounded. Sadly, no. If you go up to 4 dimensions, where you've now got 16 balls, the ball right in the middle is as big as the ones around it. And in 5 dimensions, it's bigger. And by the time you're in 10 dimensions, that ball inside the unit balls, inside the box, is bigger than the box. And once you're up to 26 dimensions, it's more than twice as big as the box. Our intuition doesn't work, and this is not a rigorously correct way to say this, but in higher dimensions, a ball, even though it's still the set of all the points that are within 1 unit radius distance from the central origin, the balls become spiky, is one way to think of it. It's a weird distribution of where the content is. And there's an area of mathematics called measure theory, which is all about trying to understand these shapes and calculate how much of them is where. These coins started as a simple example of how data can be visualized in multiple dimensions. And in the citation, you heard mention of large language models. And when you've got these big data sets, they are effectively multi-dimensional objects which we need to understand. And Talagrand's work was revolutionary in understanding these shapes and finding aspects of these high-dimensional distribution spaces which were well behaved, and then putting bounds on how far away from the mean, for example, a certain percentage of the total measure of that shape is likely to be, because the law of large numbers still applies to these higher dimensional shapes. When we mention the concentration of measures, that's a more abstract, generalized version of that, and Talagrand's work was fundamental in us having a better grasp to understand these spaces. Finally, I'm going to attempt the most simple explanation in which spin glass makes sense. And spin glass is not like glass, it's an arrangement of matter that I'm representing with these tokens. And on each one, I've got an arrow. So these are little magnetic moments within the material. And if this was a ferromagnetic material and you apply an external field, it would cause all of these to line up. And that happens with a spin glass. You apply an external field and all the little internal moments line up. Now, a ferromagnetic field, they would stay like that even when you take the external field away. A paramagnetic material would immediately, well, almost immediately, return to disorder, exponentially fast. A spin glass, however, once you remove the field, it does start to rearrange. These little moments become random, but not completely random. They're still interacting and they're interfering with each other. And it's not an exponential decay like a paramagnetic substance. It's an unusual and difficult to predict decay. And physicists were trying to work out what they could understand about this unusual state of matter. Things like how much free energy does it have? And they came up with some limits and some thresholds, but it was Talagrand's work that was able to put those thresholds on a firm mathematical foundation, taking his approach of simplifying and using randomness and probability theory to give an insight and prove what the physicists had discovered. So hopefully, using counters, coins, and dice, I haven't too oversimplified the incredible work that Talagrand was doing, but I've managed to give you a bit of an insight, a rough context for the phenomenal work they were doing. Michel Talagrand has been informed that they've won the Abel Prize, and they've very kindly taken some time to answer our questions. So, Michel, my first question for you is, given how prestigious this prize is, how did you feel when you first found out you'd won it?
Well, that's very interesting because the proper answer is I had no thought. There was a total blank in my mind for several seconds. If I had heard that the alien mothership had landed in front of the City Hall, I don't think I would have been more surprised. I had never ever thought that this could happen. So it was a shock. Pleasant shock, of course, but a very deep shock. I'm not over it yet, of course.
As we have already heard today from the citation, you've done an incredible range of work across different areas of mathematics and some physics. I'm curious to know, though, which part of your work are you the most proud of?
In some sense, I could be proud of the things which were the hardest to do, but it's a little bit different. The first result which I proved, which really had an impact, was on Gaussian processes, and this sort of miraculous result, which proves the equivalence of two very different ways to look at some object are in fact the same. And when this was done, it was such a miraculous result that I say, okay, the miracle will not stop there. Let us dream what in the same direction, what could be the structure of other related objects. And I made a series of conjectures totally out of fiat. There was not a single element of proof or real indication, just dream wish. Let us dream what things be. And so that set up a program, and amazingly enough, 2 years ago, this program was entirely completed with, of course, the help of many other people. So now there is this complete description, and all the miracles turn out to be true. The universe in that very small corner turned out to be as simple as it could be. So it's nice. It makes me really happy when I think about that.
Today you are the prize winner, but for a long time you've offered prizes, cash rewards on your website for people who can solve open problems. Could you tell us a bit more about those?
That's a good question because there are many interesting stories. Paul Erdős, who was a great mathematician, was famous for offering cash rewards, but what he would do, he would offer $15 for an incredibly hard problem. Well, I'm proud to say that in my youth I solved a couple of problems asked by Paul Erdős, but there was no cash reward for these ones. In my web page now there are 5 or 6 problems for which I offer $1,000. These problems are problems I thought about them and I couldn't solve them, and I think they are good problems. I hope that now people will look at them. One prize I offered, a significant amount of money, was $5,000, but it was for a problem over which I worked intermittently, of course, for maybe 15 years, and I couldn't solve. And my feeling was that this problem was absolutely fundamental, probably because it dealt with a very basic object, and I always had the philosophical belief that it's important to completely understand the very simple object before you try to understand the complicated one. It was solved in 2011 by Rafal Latala and Witold Bednoz, and I was so happy to give away $5,000 for that result. The proof is the most beautiful proof of mathematics I've ever seen. And incidentally, it could be it's not the correct proof. It's too complicated. So one goal I have for young probabilists, find a proof of that result that you can explain to your grandmother, like Feynman would say. A proof which the approach, you get a good idea, which makes the proof transparent, which is not now. And my intuition that this result was central was correct, because it turned out to be the essential cornerstone to finish the program that I was talking about in the previous question. So I'm so happy I gave that prize away. Now, 5 years ago, I received the Shaw Prize, which had 1.2 million money coming with it. I have donated the entire amount of that money to create a foundation which will distribute prize for results in mathematics in the areas which I have worked and which I understand, which goes well beyond probability. And this foundation will start within 10 years to give very significant prizes in mathematics. And the money of the Abel Prize is going to join the money for the Shaw Prize, exactly. I'm going to donate the entire amount to the same foundation. So when the first prize comes out, you will have a very, very interesting story to tell.
Thank you so much for taking the time to join us, Michel. And once again, congratulations on an incredibly well-deserved prize. This year is the 22nd year of the Abel Prize, so we're joined once again by Lise Øvreås, the president of the Norwegian Academy of Science and Letters, who's going to give us some more background information about the prize.
Well, the Abel Prize was established by the Norwegian Parliament in 2002 on the occasion of the 200 years anniversary of Niels Henrik Abel's birth, Norwegian's greatest mathematician throughout the times. And the Abel Prize exists to honor individuals, of course, but in a larger context also stimulate interest among mathematicians in society and stimulate young people. I would like to thank the Abel Committee for their excellent work.
Now that we've had the announcement and we know that Michel won the award, what happens next? How does he get his award?
Well, it is a pleasure for me to welcome you all to the Abel Prize Awards ceremony at the University of Ola in Oslo on 21st of May at 2 p.m. Norwegian time. Michel Talagrand will receive the Abel Prize from His Majesty King Harald V. There will also be a lecture in honor of the laureates at the University of Oslo on Wednesday, 22nd of May. Registration will soon be available through our website. You are most welcome to celebrate this year's Abel Laureate with us in Oslo.